Oh, looks like we're at time. So welcome everybody. My name is Gord Farrell. I'm the president of the RASC Vancouver Center. So thank you all for coming to our monthly lecture. Yeah, so we'll go through some of our regular business and then we'll bring on our special speaker for the night. So yeah, since this is our more than our usual lecture, I'll just do a little brief summary for those who aren't familiar with what the RASC is. It's the Royal Astronomical Society of Canada. It was started in Toronto in 1868 and went national in 1903 after getting royal assent from the King at the time. It's over 5,000 members across Canada with 30 centers from St. John's to Victoria, and there are 6 here in BC. And our mandate is public outreach and education for astronomy. So we do have some upcoming events I should mention. Well, generally just one. So we have virtual International Astronomy Day and Science Rendezvous with SFU coming up in May. So it'll be on Saturday, May 8th from 11 to 3. Registration is through Eventbrite. There's a link there, which you'll be able to find on our website soon. SFU is handling all the registration for this. So we'll have a couple of speakers and I'll do a short online presentation looking at the sun through a telescope. Hopefully there are clear skies for that. And for anyone who's being picky, yes, it's not officially International Astronomy Day, but we're working with SFU, so we're unofficially moving it up a week. So we are always looking for volunteers. I mean, granted, in the time of COVID, we're not doing a whole heck of a lot, but yeah, RASC members only can volunteer for our events when we get those things going again. Our national organization also provides a number of publications, various books, and for various ages. There's also teaching guides for any teachers out there who want to teach astronomy to students. For people who do observing, the national organization offers a number of certificate programs. So if you want to tick off a list of objects, you'll get a special certificate acknowledging that you've done so. I also do double duty as the editor of the Nova newsletter. So we're always looking for articles. So if anyone has anything they'd like to write up, you can always send it to me at the Nova editor address right there. That's also available on our website. So yeah, if you like what you see, you can always join us. You can approach our membership directors, Susanna and her assistant Marla, to join up. When you join up, you'll get Sky News Magazine, the Annual Observer's Handbook, which is really good. We also have a telescope loaner program, so you can speak to our director of telescopes about that. And you also get access to our extensive library and use of the Trottier Observatory and the Anthony Overton Memorial Observatory in Maple Ridge. Fortunately, those last two are under suspension right now because of COVID. So hopefully we'll get those back up and running as soon as the vaccinations and the virus allow us. So a few words about Paul Sykes. So today's lecture is the Paul Sykes Memorial. He was born in Pennsylvania in 1918 and was interested in astronomy at an early age and published his own monthly column in the local newspaper. He was an officer in the US Air Force, serving during World War II, where he received a number of medals and citations. And following the war, he moved to Vancouver and attended UBC, earning a degree in physics in 1948. He later rejoined the Air Force and was a part of the NERVA project for nuclear rocket development, and later returned to UBC when he was appointed a lecturer and administrator in the physics department and remained there until his retirement in 1983. He was a life member of the RASC and an avid supporter, and passed away in October 2005 at the age of 87. So with all that out of the way, I'd like to introduce tonight's speaker. So we're happy to have Dr. Phil Plait, who many of you may know better as the Bad Astronomer. He describes himself as an astronomer, author, sci-fi dork, TV documentary talking head, and all-around science enthusiast. He has worked on the Hubble Space Telescope And he's hosted the series of Crash Course Astronomy videos for PBS Digital Studios, and also has a blog on the Sci-Fi website. And he's here tonight to talk to us about strange new worlds and whether or not the Earth is special. So with that, I will stop my share and hand it over to Phil.
Thank you, Gordon. Can you all hear me?
Yep.
Yes.
Excellent. Thank you so much for having me give this talk tonight. It's a pleasure and an honor to give the Paul Sykes Memorial Lecture. Also to speak for the RASC. I have spoken for the RASC before. I want to say in Calgary. I love Canada. You may be impressed that I speak Canadian. I learned it watching SCTV while I was a kid, and then brushed up watching Stargate as an adult. So I'm very fluent in it. It's wonderful because I can use the metric system giving this talk. Yay! So that makes me very happy as well. The only regret I have is that I'm not there in person. Every time I go up to Canada, I have a lovely time, and I wish I were there. I like Tim Hortons. I like Timbits. Okay, so let me share my screen like this and hit play. And now you should all see my title slide, I hope.
Yep.
Looking over and hearing yeses and seeing nods. So excellent. Great. So I'm going to be talking about exoplanets today. And these are alien planets orbiting alien stars, something we did not know about. What is this, 2021? So say 30 years ago. 30 years ago, the first ones were just being discovered. They weren't announced until the next year. Come a long way since then. Quite a bit to talk about here. In fact, one of the things I love about exoplanet science is back in the day when the first ones were being discovered, and I'll talk about how that happened. Every time a new one was found, it was a big deal. You know, we found one orbiting this star, and we found one orbiting that star, and it's wow, it's so amazing. Now it's like every day. It's like, you know, here's another one, throw it on the pile. But there was a time when we had dozens, maybe even hundreds, and we were able to start categorizing them. And for me, that was when this started to become a real science. It wasn't just, you know, we found one. Now, when we're starting to say, oh, here's one that is orbiting this kind of star, and it's this kind of planet, then you start to categorize them. You can start looking for trends. And when you start looking for trends, that's science, because trends are telling you something's going on. There's some physics happening. So that was a very exciting time, and I'm gonna talk about that here. But the beauty of all of this is that by finding all of these planets, we are able to put our planet in context. The question is, of course, I'll phrase it a different way. One of the things we are trying to do, of course, is find another Earth. We want to find a planet that looks like ours, because as far as we know, the Earth is the only kind of planet that has life on it. Now, there could be all kinds of different kinds of life on all kinds of different planets. However, we only have one example of a planet with life. That's us. So we look for planets like our own so that we can hopefully find life, something like as we know it. So that the question then becomes, is Earth special? Is there something special about our planet, or are we finding zillions of planets like it? And it turns out the answer to this question, as you will see, is no, maybe, yes. It depends on how you ask the question. What do you mean by special? And that is the theme of tonight's talk. So let's start with the planet we know best, Earth. This is Earth. Pardon me, it's been very dry today, so I will be probably clearing my throat and drinking lots of water. I apologize that for in advance. This is a view of Earth from the Discover satellite, which is about 1.5 million kilometers towards the sun, looking back on Earth. And it takes images, several images every day, and monitors our planet. Looks at climate change and all kinds of things like that. This is a fairly standard view showing Africa there, Europe, Saudi Arabia, and Asia. When you think of the Earth from space, this is sort of the thing you think of. Maybe you think of North America and South America and Central America, that sort of standard image. However, if you want to think about the way the Earth is typically, it looks more like this. I love this picture. This is taken when the Earth was presenting the middle of the Pacific Ocean towards that satellite. If you look off to the right, the upper right, you can see North and Central America, Baja California. Down to the left, Australia, a little bit tough to see. That's pretty much it. You know, Hawaii's in there, some other islands in there. They're too small to see. And Antarctica is there at the bottom. You can barely see it. When I say this is a more typical view, it's because Earth is, in many senses, a water world. Our surface is 70-something% covered in water. And the Pacific Ocean is enormous. And I don't think people truly appreciate that almost half the planet is covered by this ocean. I flew to Australia some years ago, left San Francisco. In 10 minutes, I was over the Pacific Ocean, and like 13 hours later, came over the coast of Australia. So that's a big ocean. I was over it for half a day flying in a jet. So yeah, that's how I think of the Earth, as a water planet. And you can see there are 3 different states, 3 different phases of water there. Blue, liquid water, of course. The white is mostly clouds. But at the bottom, just a sliver, you can see a little bit of Antarctica there. That's solid water, right? That's water as ice. And it turns out this is important. Life as we know it needs a lot of stuff. It needs energy input, and we get that from the sun. It needs air. That helps our chemical processes. But we think that to arise and to sustain itself, life needs water. And that's because water is a pretty interesting chemical. It freezes, it melts, it turns into a gas like anything else, but it has a very broad range of temperatures. It can stay liquid. It can be in all 3 of these states at the same time on Earth. That's important because what happens is it can snow or melt. The ice will turn into water. That water evaporates, moves across the planet, and rains down. And then that forms lakes and rivers, and that flows back into the ocean. And that cycle repeats. That's called the water cycle. And that can carry things from one place to another on the planet. Water is a great medium. It's a great source that if you put things in, like minerals, it can mix them up and they can interact with each other and become more complex and form more and more complex molecules that eventually become life. We don't know exactly how that worked, but that's kind of the picture. We know that there were some complex molecules that existed in the early Earth. They got together, they were fruitful, and they multiplied, and water was there for that whole story. So when we're looking at other worlds, one of the things we want to look for is water. Keep that in mind. So in our solar system, is the Earth special? Well, let's look at the other planets in our solar system. I love this painting. It's beautiful. It shows the sun and the planets. The sizes are to scale, the distances are not, which is a good thing because we'd be cooked if we were that close to the sun. The sun's about 1.4 million kilometers across. There are 4 planets close to the sun, the rocky Earth-sized terrestrial planets, Mercury, Venus, Earth, and Mars. The outer 4 planets, Jupiter, Saturn, Uranus, Neptune, are huge gaseous giants, and you can subdivide them into different kinds. I'm not going to worry about that. Because I'm just looking at the big picture here. And the big picture is those 4 big planets probably cannot support life like us because they don't have a solid surface. They're mostly gas going way down into their atmosphere. And by the time you get down to something that's no longer gas, the pressures are huge, the temperatures are huge, and you can't have life as we know it. Mercury, too hot. Venus, hotter. Venus, like the worst place in the solar system. Atmospheric pressure at the surface is 90 times the Earth's. That's like what the pressure you'd feel being a kilometer down underneath the ocean. So tremendous pressure. The atmosphere is carbon dioxide. It's like 450 degrees Celsius on the surface. I don't remember the exact number. It has clouds of sulfuric acid. It's basically hell. It's a terrible, terrible place. And then there's Mars, smaller than Earth, but it has a thin atmosphere. It's too cold. It has lots of water, but it's all frozen. Or it's buried underground. There's probably, they've actually found some evidence for liquid water on Mars, but it's in subsurface lakes. That's a relatively new discovery. And I should probably add that to this talk now that I think about it. But as that is, you can see that there are 4 planets kind of like Earth. So in that sense, Earth isn't terribly special. On the other hand, those 4 planets, you don't include Earth, of the 3 other planets, they're not terribly Earth-like. So in fact, in our solar system, the Earth is special. But the question is, what about other solar systems? Well, we didn't have the ability to answer that question until relatively recently. And when I think about relatively recently, I'm talking about 30 years ago. I was already doing astronomy. I was a professional astronomer at that point in my life. And I should add, I meant to say this at the beginning, I love astronomical societies. I love amateur astronomers. I consider myself an amateur astronomer. Even when I was doing the professional research, which I don't do anymore, I considered myself an amateur astronomer. And now even more, hauling out my scope and looking at stuff in my backyard. So that is a near and dear thing to do in astronomy for me. So thank you all again for inviting me. So I realized, as a matter of fact, when we started discovering planets, that, yeah, it took professional observatories at first, but after a while, it became that you could actually get off-the-shelf equipment and see the evidence for them yourself. Well, let's talk about that evidence. This is not the first way these planets were discovered, but it is the most successful way, and this is called the transit method. Now, if you have planets orbiting stars, if they're orbiting this way, this method doesn't work. You have to be seeing the orbit edge on. If the orbit is edge on, then every orbit, did that wrong. Oh my gosh, everything. Oh, don't panic, everybody. Hold on. There we go. Hit my space. Nope. There we go. Very, very touchy controls here. If you have a planet orbiting a star, once every orbit, if you're seeing that orbit edge on, it passes directly in front of that star. You get a mini eclipse, what we call a transit. When that happens, it blocks a little bit of the star's light. So if you're measuring the star's light, and that's what that graph is there on the right, you're measuring that star's light, there's a little bit of noise, it's going up and down. When that planet passes in front of the star, and I have to start the animation again, so who knows what's going to happen here. It worked. When the planet passes in front of the star, there's a sudden drop in that light until it passes the star and then it goes back up. So that's your transit. Typically, a planet like Jupiter and a star like the sun, that planet will only block 1% of that star's light. Is that right? Wait a minute. 10, 100th. Yeah. So it blocks 1% of the star's light. A planet like the Earth blocks even less. So this is not a huge drop. Even a big planet and a small star, you're just talking about a few percent. So you have to do this fairly accurately. However, go out and buy yourself a 25-centimeter telescope, get a nice digital camera to put on that, and you can do this yourself. You can point your telescope at stars and measure this. The data is not going to be as great as it is with a big telescope, of course, but you can do this for yourself. And when I realized that early on in the game, I was pretty amazed. This method is phenomenally successful. And the beauty of it is that you can launch telescopes into space. They're very stable platforms. You can keep your detectors at a constant temperature. There's no atmosphere to mess things up. And so you can measure these dips in stars very, very accurately. The good thing about this method is that it tells you the size of the planet. The bigger the planet, the deeper the dip. If you know how big the star is, and we usually know that, we can have ways of measuring that, or we can use physical models to get that, we can get the size of the planet. And so that's great. You know, the bigger the planet, the more it blocks the light. So from this method, you get the size of the planet. You also get the orbit of the planet, because how long it takes to pass in front of that star tells you how big its orbit is. There are ways of calculating that. It can also give you the shape of the orbit in some cases. So you can really learn quite a bit. If you know how far it is from the star, and you know how hot the star is, you can also estimate the temperature of the planet. And I'll get back to that in a moment. So this is a very, very powerful method. There's another method called the reflex velocity, and this is something you're probably familiar with. It's similar to having a big kid and a little kid on a seesaw, or better yet, if you have two people facing each other, somebody who's big and somebody who's little, and they're holding hands, if the big person swings the little person around, that big person is actually going to make a small circle as the little person is making a bigger circle around them. The more massive object doesn't move as much as the less massive object. You might think of planets as orbiting stars, but really they orbit their common center of gravity, their center of mass. And we call that the barycenter. That's the technical term for it. And you can see that here on the left in this terrific drawing. I don't see any reason to make this more sophisticated. 8 bits works just fine for this. You can see a planet orbiting a star, and as the planet goes around, the star is making a smaller circle. That doesn't help you much if you're seeing the orbit face on like that. But again, if you're seeing the orbit edge on, then you don't see the planet. We're not actually physically seeing this. Typically, stars are too far away, and as the planet goes around, you don't actually see that motion. But that star is making a circle. So sometimes it's heading toward us, and sometimes it's heading away from us. And if it's heading toward us, its light is going to be blue shifted. There's a Doppler shift. And when it's when it's heading away from us, its light is red shifted. This is the same thing as when a motorcycle goes past you and you hear that, the sound waves are sort of like light waves. The pitch of the sound is compressed and gets higher when it's heading toward you, and it's longer. They're stretched out when it heads away from you. So you have that, the Doppler shift is the same thing, but with light. So if you can point a telescope at this star and measure precisely the colors of the light it's emitting, you can see, and if there's a planet orbiting it, you can see those colors shifting a little bit. This is an extremely difficult thing to do. You have to have extremely precise measurements. But I'll say that this is how the first planets were discovered. At least the first planets like around stars like our sun. That's a whole other thing. The first planets weren't found around stars like the sun. That's a completely different lecture. But the fact is, the beauty of this is that this also gives you the period of the planet, because you can watch the colors go back and forth on that star, and how long it takes to go one way and then the other. That's how long it takes the planet to go around. But also how much that star is moving depends on the mass of the star and the mass of the planet. So if you're seeing a system like this edge on, if you see a transit, you get the size of the planet. If you can use this, what's called the reflex velocity, to get the mass of the planet with the mass and the size, what you can get now is the density. And that's the key to everything, because different things have different densities. Water has a density of 1 gram per cubic centimeter. We can just call that 1. Rock is about 2 to 3 times that much. Iron is 10 times or 8 times that much, I think. Gas is much, much, much less. So when you look at the densities of the planets in our solar system, Earth is around 5.5. It's a mix of mostly metal and rock. Jupiter's about 1. It's got about the average density of water, but it's huge, which means that really it's mostly gas. So just by knowing the density, you can immediately tell whether you're talking about a gas giant or a big rocky planet or whatever. So these two methods together are really extremely, extremely useful and powerful in finding other planets. We have launched a couple of telescopes to do this sort of thing, actually more than 2. Kepler was one that NASA launched a few years ago. It ran for a few years looking at one spot in the sky, just staring at stars, waiting for them to just get dim over and over again as the planets transited. Found thousands of planets. TESS is the Transiting Exoplanet Survey Satellite. Yes, that's correct. And that's scanning the whole sky, looking at all the stars in the sky over and over again. It's basically sweeping around, rotating around, looking at all the stars. And it's also found quite a few planets. I'm not sure how many it's found right now, but when the whole thing's over, it will have found thousands as well. Gaia is a European satellite, wasn't really designed to find planets, but it is possible to find planets with it. So we have tons and tons of ways of doing this. And as of right now, there are more than 4,000 planets like this that have been discovered, over 4,000. They used to be called extrasolar planets, planets beyond our solar system. That's now been kind of shortened to just exoplanets, which means outside planets, planets outside our solar system. Plus, just an awesome word. Any word with X in it's going to be fun to say. Very science fiction-y. There is another method that I just want to mention because it's awesome. And that is literally directly seeing planets. You get direct images of them. You just point your telescope at them and you can see them. It's obviously not that easy. This has been done many times. We have images of many, many planets. The best way to do this is to look at young stars that are just a few million to a few tens of millions of years old. These planets, any planets that form around it, will be young. If they're young, they still have a lot of heat left over from their formation. Basically, planets form by asteroid impacts, right? These asteroids come in and hit each other, and this thing grows and grows. That generates a lot of heat. As you know, if you've seen any movies, you know that big asteroid impacts generate a lot of heat. So what you do is you look in the infrared, because that's where these planets are glowing. That has another advantage. Stars tend not to be bright in the infrared. And also, you can get really good high resolution images this way. So these are images of the star Beta Pictoris, a southern hemisphere star, pretty bright, naked eye star. They block the light of the star with what's called an occulting disk. It's just literally a piece of metal in the telescope that blocks most of the light from the star, and that reduces the glare, and it helps you see fainter things near it. Also, the centers in these images, the star itself has been blocked, literally just masked out like with Photoshop, so that you're not distracted by all that junk. Now, upper left, November 2003, there's that bright spot. That is a planet orbiting Beta Pictoris. You can see in the next image on the right there at October 2009, where it used to be as marked there, 2003, but now you can see it's on the other side of the star down there at about 5 o'clock. And then another image was taken a few months later on March 2010, and you can see it's moved even a little bit more. In that bottom image, you can also see Saturn's orbit seen to scale. This planet orbits Beta Pictoris almost edge on. We almost see it edge on. It's tilted just a little bit. People looked for transits of it recently when it passed in front of the star and nothing was seen. That was unfortunate, because it would have been nice. But this works really well. And in fact, this method has been done for quite a few stars. This one's HR 8799, another young star. This one has 3 planets, B, C, and D. I'll add that when we discover planets, they are named after their star's name, and then a lowercase b for the first one discovered, and then C, D, E, and F. It's not an order of distance from the star. It's not like Star Trek where you're going to go to, Rigel 12 and you can know that's the 12th planet out. It doesn't work that way. These are named in order of discovery, and they skip A because typically A is used for binary stars. So if you had 2 stars, it would be, I don't know, Hector A and Hector B. It gets very confusing. I just made that name up. So the thing is, they just skip A and go right to B. There's all kinds of reasons for that. So there's actually a 4th planet orbiting HR 8799. So that would be E. And in fact, you can see it in this animation, which is one of the coolest things ever, taken over 7, 8, 9 years. I can't remember, 2011, 2016. So it's taken over 5 years, and you can see the planets moving. Let me repeat that. And you can see the closest one in there is right there at about the 3 o'clock position, but you can see them actually physically orbiting the star. That's just phenomenal. And from this, they're not transiting and we're not getting any reflex velocity out of them. However, if you can trace them long enough, you can actually figure out what their orbits are, if they're circular or ellipses, how they're interacting with each other, all kinds of stuff. So this is just phenomenal, the technology that we have at our disposal now. Just great. So that's how we found planets. There are other methods too. I won't go into them. They get more and more subtle as you dive down. But I think there's like a dozen different methods. If you woke me up out of a cold sleep, I think I could name 7. And some of them are very complex and subtle. But those are the big ones. So now we're finding these planets. Are they like Earth at all? Are we seeing planets like we see in our solar system? Well, we have to go over just one more sort of topic, one more concept, and that's called the habitable zone. This is, very generally speaking, this isn't a hard and fast rule, it's more of a suggestion. It's the distance from a star a planet can be where it's possible for it to have liquid water on its surface. Now, this depends on the planet. If it doesn't have an atmosphere, you're not going to get liquid water on its surface. It doesn't work that way. If it's a gas giant, doesn't really matter. Maybe. Oh, foreshadowing. However, it's a good concept in general. It's kind of just a vague way of classifying if planets, may or may not be like the Earth. So in our own solar system, Venus, Earth, and Mars orbit inside the sun's habitable zone. Venus on the inside edge, Mars on the outside edge, which technically makes them habitable zone planets. However, neither, if you went to either of these planets, you'd be dead real quick without a spacesuit and a lot of technology to keep you alive. So that's what I mean by, in general, it's just a concept. It's a suggestion. When it was first thought up, when somebody first started talking about it, and you'll still hear some people mention it this way, they called it the Goldilocks zone. And you hear that, and it's a good name because when you hear it, you kind of know what it means because everybody's heard that fable of Goldilocks and the three bears. However, when you think about it, it doesn't make sense, right? It should be called the baby bear zone, right? Because the papa bear stuff was too hot, the mama bear stuff was too cold, or whatever, too big, too small, and the baby bear stuff was always just right. However, Goldilocks was the one who basically, colonized, for lack of a better term, the bear's cabin, took all their stuff, just usurped all their facilities, and then we turn around and name it after her? I don't think so. So I prefer habitable zone. It makes more sense. If you called it baby bear zone, people would be like, what? What does that mean? So habitable zone it is. Now, politics aside, this is a pretty good concept because it's different for different stars, but it's still there. Every star has a habitable zone. For hot stars, it starts farther out and stretches much wider. For cooler stars, like at the bottom, it's much closer to the star. So if you look at a star like Rigel or Deneb, these are huge, massive, luminous stars. If you want to have a planet orbiting that star and have it be Earth-like, it's going to have to be really far out. On the other hand, for red dwarfs, for example, these feeble, low mass, extremely dim, cool stars, you have to be really close to them to be warm enough to have liquid water on your surface. This is another concept that you're kind of used to. If you have a fire, like a bonfire or fireplace, whatever, if you get too close to it, you're going to get too hot. If you get too far away from it, you're going to get too cold. The bigger the fire, the bigger that range of distance is. So if we're going to look for potentially Earth-like planets around other stars, being in the habitable zone is a good place to look. Have we found planets in the habitable zones of their stars? Yes. Yes, we have. This is an example. This is from several years ago. I like this graphic. It's easy to understand, which is why I use it, even though it's old. We have many, many, many more planets than this now. So this is just for an example. For a G star, which is a star like the sun, for example, there's the Earth. Hello, we orbit the sun. There's also a planet called Kepler 452b. It was the 452nd star to have found that the Kepler Observatory found to have a planet. It was the first planet found orbiting that star, and it's in that star's habitable zone. K stars are a little bit cooler than the sun. They're kind of orangey, and you can see all those planets there. And M stars, red dwarfs, were found to have planets too. And as you can see, these planets are scaled together. As you can see in the title there, they've been enlarged by 25 times just so you can see them there. If the Earth were to scale there, it'd be a little tiny dot. Interesting, what you can see in this graphic right away is that all these planets are bigger than the Earth. And that's an interesting thing, because what is that telling us? Is that telling us that the universe is really good at making planets bigger than the Earth? Or is it telling us that we're just not very good at finding planets as small as the Earth? And the answer is both. I'll get to that in a moment. Here are some other just examples, some artwork of some of these other planets. Some of them are as small as the Earth. We've even found planets orbiting stars smaller than Earth, not many, but some. And they get as big as Kepler 22b, which is roughly twice the size of the Earth. And it turns out at around that size, things get interesting. This is as of 5 years ago now. Again, we found many, many, many more planets than this now, but I haven't found a graphic this good. And I'm terrible with putting together graphics like this. So this is illustrative, and I like it, and it shows you the point I'm trying to make. Even if you add in all the newly discovered planets that we have now, this graph doesn't change in character that much. All it's showing you, and if you don't like graphs, that's okay. This isn't that hard to understand. The taller the bar, the more planets we found. From left to right, left are small planets, right are big planets. So when you look all the way on the left, that's Mars-sized planets, and we haven't found very many of those. Why not? they're small and they're hard to find. The transit method, they make a little tiny dip, and that's very difficult to detect. They don't make their star make a much of a circle when they orbit, so it's hard to detect them that way. We have not found that many because they are hard to detect. Same thing with Earth-sized planets. We're good at them. We find lots of them, but they're still fairly difficult to detect, especially around bigger stars. Let's skip the two in the middle there, the two big ones. Jump over that, you get to Neptune-sized. And at that point, Neptune's a big planet. It's 4 or so, I think, 4 or 5 times bigger than the Earth. That's in diameter bigger. So that's big enough to start making a pretty decent sized dip in the star in the transit method. So we're good at finding those. The next three are sort of between Neptune and Jupiter, and then Jupiter sized and bigger than Jupiter. Planets don't get much bigger than Jupiter. They tend to turn into stars when they get bigger than Jupiter. But here's the thing, Jupiter's a big planet. Like I said, it creates a 1% drop in the sun's light if it transits. So finding those is relatively easy. If we look at a star and it has a Jupiter-sized planet orbiting it, we're going to find it, unless, you know, the orbit's not edge on, or it's orbiting really far out and takes too long to go around, whatever. The point is, if it's to be found by the transit method, we're going to find it. And the point is, we're not finding as many as those two big bars in the middle. The one on the left is what we call super Earths. These are planets that are roughly a little bit bigger than the Earth, maybe 20% bigger, up to about twice the diameter of Earth. And then, or yeah, about that. And then the next bar, the big one, are what we call mini Neptunes. It's labeled sub-Neptune. Tend to call them mini Neptunes now. That's more preferred. And these are bigger than twice the radius of the Earth, up to about 3 to 4 times the size of the Earth. And that's a smaller than Neptune. The reason we put these into two different bins is that up to about twice the size of the Earth, we think that you can still have an Earth-like planet. It can have rock and metal in an atmosphere like the Earth. But once it gets to about twice the Earth's size, when it's forming, it's massive enough to start drawing in lots of gas as it's forming, and it jumps immediately to becoming a gas giant. So right around there, you don't see a lot of planets right at about 2 times the size of the Earth. They go from about 1.9 right up to much bigger. And so they become more like Neptune. So that's sort of the dividing line there. So super Earth's over here. Well, let's see, wait, you're flipped for me. So super Earth's over here, Neptune over there. And we're finding lots of those. These are not the easiest planets to find, but by far, they're the most common ones we can find. And that's telling us that the universe is good at making them. These super Earths and mini Neptunes are the most common kinds of planets in the galaxy, if not the universe. And that is interesting because that brings us back to my original question, is Earth special? When you look at our solar system, we don't have a super Earth or a mini Neptune. We go from Earth to Neptune. Now, there may be another planet out there, Planet 9, which is orbiting way out past Neptune. There's some evidence for it. It's complicated. If it exists, it may be a super Earth or a mini Neptune, but we don't know if it exists for sure. But as of right now, we don't know that the solar system has one of these. That's peculiar. Why not, when most stars that we see make planets like this? So in that sense, our solar system is kind of special because we don't have the most common kind of planet. Does that make it important? Is that an important thing? Do we have an Earth-like planet because we don't have super Earths? Nobody really knows. There is an idea that we used to have super Earths orbiting close to the sun, but their orbits were unstable. They collided, basically blew themselves to bits. A lot of that material was either lost or fell into the sun. And what was left over formed the 4 inner planets. And that's why they're so small compared to the other planets in the solar system. And that's why we don't have a super Earth or a mini Neptune. It's an interesting idea. Nobody knows if that's correct or not. So either way, we don't have them, and that's interesting. Oops, went too far. So we are finding Earth-sized planets. We're finding them with Earth masses. We're finding them in the habitable zones of other planets. That's all we know. If you see a headline that says astronomers find Earth-like planet, yeah, put on your skeptic hat, because what they're really finding is probably an Earth-sized planet. It may even have a temperature roughly like Earth's, but that's all we know about it. We don't know anything about its atmosphere, if it even has one, how much water it has, if it even has any. So, is it Earth-like? We don't know. We just know that it's probably in its star's habitable zone and the size and a few other things. But this brings up an interesting question. Was Goldilocks too picky? Yes, we've all heard the story. Yes, she was. But should we broaden our terms a little bit? Is the habitable zone the be all and end all of planets that could possibly be habitable? And the answer is no. And the picture in front of you is a big hint. That's Jupiter. Love this picture. You can see two moons down there at the lower right is Io, the volcanic moon, completely uninhabitable, terrible place to be. It's constantly erupting in volcanoes. It's buried in Jupiter's radiation belt. It's too cold, doesn't have an atmosphere, But at the lower left is Europa. This is a close-up image of Europa, roughly and very roughly the size of Earth's moon. It's unusual. It's covered in ice. That's what all that white stuff is. That is ice. Think of Canada in winter, and you're close. Except it's even colder in Europa. All of those cracks in its surface look kind of like, if you've ever seen a lake and the ice will crack and it'll get a seam in it. All that red material, possibly complex carbon molecules. Sunlight hits simple molecules like methane, breaks them up, and they recombine to form more complex molecules. And these tend to turn reddish, brownish, yellow, even black sometimes. So when you see red colors like that in the outer solar system, it's typically these kinds of molecules. And they settle into the cracks and grooves and everything on Europa. And the thing about Europa is that's water ice. That is actually ice made of water. And in the 70s, it was hypothesized that Europa might have an undersurface ocean. And it turns out it does. We now have tons and tons of evidence for it, that it actually has an undersurface ocean under that a thick ice shell. There's actually more water under the surface of Europa than there is on the surface of the Earth. It actually has more water. And it turns out it's kept warm due to complex interactions with Jupiter. As it orbits Jupiter, Jupiter's gravity sort of compresses it and squeezes it. It extends it and compresses it. And that generates friction inside the moon. Friction generates heat, and heat melts that ice and you get water. Europa probably has a rocky core. And that's interesting because that core is going to be hot. So it may have undersea vents like the Earth does, these cracks in the Earth where magma or whatever, boiling water comes out, horrific chemicals, but there's life around these vents on Earth, these hydrothermal vents. There might be something like that under the oceans of Europa. We do not know. It's something we really, really, really want to explore. So that's really interesting. Here you have an icy moon of a giant planet, 1 billion kilometers from the sun, roughly, and yet there could be the condition. Well, we think there are conditions conducive for life, and there may be life there. We just don't know. Another moon, Enceladus. This is a moon of Saturn. Again, look at it. It's all water ice. Interestingly, it doesn't have very many craters. Neither does Europa. You don't see a whole lot of craters there. Enceladus has that region there at the top with lots, but you can see in the southern hemisphere, not very many. And we think that's because it gets resurfaced. Basically, it's being repaved constantly. There's water from, it has an internal ocean as well. This water comes out on the surface. And if you get an impact that makes a crater, that eventually will fill with water and get smoothed over. Those stripes at the bottom, those bluish stripes, they're called tiger stripes, like a tiger clawed Enceladus there in the southern hemisphere. Those are cracks. And as it orbits Saturn, again, Enceladus stretched and squeezed. Those cracks open up and close and open up and close when that happens. The pressure, the water is under pressure, and it shoots out of these cracks and forms geysers. This is an image from Cassini, the Cassini spacecraft. That last one was as well. This is, the sun is behind Enceladus. So you're looking at the dark night side of Enceladus. On the right there, it looks bright. It's being lit by Saturn. That's Saturn being bright in its sky, lighting up the surface of the moon there. That's as romantic as it gets, my friends. Imagine standing there, looking around you by Saturn light. Oh my word. But the sun is on the other side, and those geysers are shooting water up into space, and they're backlit. You can actually see the shadow of Enceladus there curving off on the left-hand side on that spray. Cassini flew through those geysers. They are water. They have some heavier molecules in them that we think may be organic, and that means just carbon-based molecules. So it has all the ingredients it needs for life. Are there alien fishies swimming under the ice shell of Cassini? We do not know. Really, really would like to find out. And that's not all. Not just Europa and Enceladus. There's Rhea and Titania and Oberon. These are orbiting Uranus and Neptune. Triton, the Cantaloupe moon. That actually has nitrogen. They're essentially geysers. Geysers are technically only supposed to refer to water, but there's nitrogen shooting out of Triton like Old Faithful. So we know that it too has sort of this undersurface activity. The distant object, a trans-Neptunian object, this thing that orbits out past Neptune, Eris and Sedna may also have undersurface oceans. There are calculations that show that. These are relatively big objects, roughly Pluto-sized. Speaking of which, Pluto might have an undersurface ocean. Pluto, 4.5 billion kilometers from the sun. That heart-shaped region there called Tombaugh Regio, the left-hand side is called Sputnik Planitia. It too is smooth, no craters, which means it's being resurfaced. They think that's nitrogen ice. There's possibly a liquid water ocean underneath Pluto. On top of that is a bunch of very sluggish, gooey nitrogen with the consistency of like toothpaste. And it's warm at the bottom and cold at the top. So that stuff is rising and cooling and then falling again. It's convecting. That's what's resurfacing that area of Pluto. So that's indications again that there's liquid water in Pluto, the last place in the solar system I would have guessed. So there could be liquid water in other places. So Goldilocks may have been too picky there. What about not water? Could something else replace water in our search for life? And the answer is yes. There's an image of Saturn from Cassini. That big orange tennis ball sitting in front of it is Titan. The rings are edge on there. This is an actual image. The rings are edge on, so they look like a sharp line. Titan is huge. It's the second largest moon in the solar system after Jupiter's Ganymede. It's a little bit bigger than the planet Mercury. If Saturn weren't there, we might consider Titan a planet in its own right. It has a thick nitrogen atmosphere with about 1.5 times the surface pressure that Earth has. It's lower gravity. It's very cold, but it's an interesting place because with that atmosphere, it can have liquids on its surface. Not water, because water would be frozen as hard as granite is here on Earth. But using radar, Cassini could penetrate the hazy atmosphere of Titan. And it uses radar in a similar way that a cop does when you drive past them. They use the radar gun. It sends little pulses of radar down and times how long it takes for them to get down and then back up. And if it hits a mountaintop, it takes a little less time to get down that far and back up because the distance is lower. If it hits a crater or a valley, it takes a little bit longer. So by timing this, you can map out the surface of Titan. But near the North Pole, it got these big black regions where basically radar was not returned. That means the radar was being absorbed by something. You send that ping down, it's gone. What absorbs radar? Liquids. What can be a liquid on the surface of Titan? Methane. That is right there. Is that Kraken Mare or is that Ligeia? I think it's pronounced Ligeia. I'm not good with these names. But this is a lake. It's as big as the Great Lakes. Bigger. In fact, it may have more volume than Lake Superior of liquid in it. And look at it. It's a lake. I mean, you'd look at that right away and go, oh yeah, sure. Look, there are highlands around it where the methane will evaporate off the lake, blow out over the mountains, the highlands there, the hills, rain down, and then find its way back down to sea level. And that's what all those tributaries there you see at the lower left and upper right, and so at the lower right as well. That's the same thing as the water cycle on Earth. It's just using methane. Methane is a carbon compound, a simple one, but it's carbon. So if there's a source of energy on Titan, and there's sunlight and all kinds of other things, you might be able to make complex molecules on Titan. It would be methane-based, not water-based, but could there be life on Titan? The answer is, maybe. Or I should say, yes, there could be life on Titan. Again, we don't know. All right, let's broaden our horizons a little bit more again. What about Mars? We look at Mars now. It's pretty dry. There's not a whole lot of water ice there. Very thin atmosphere. It's quite cold. The ice is locked up in the polar caps. It's underneath the surface at mid-latitudes. But there's tons of evidence that there used to be a lot of water on Mars. We look at it now, it's kind of dry and dead. You look at it 3.5 billion years ago, it's possibly covered in water. We don't know if it was liquid water. It might have been glaciers. There's a lot of arguing about that right now. There's interesting evidence going both ways. But there's tons of evidence, and by evidence, I mean, we see riverbeds. You can see these dry riverbeds. There's evidence of oceans. Curiosity, the rover, is sitting in a crater that used to be a lake. It's got tons of clay in it, dried out clay, but for clay, you need water, liquid water at some point. So clearly in the past, Mars may have been more Earth-like. And in fact, Mars may have been more like Earth is now back then than Earth did back then. We didn't have an atmosphere like we do now. We don't know how much water was on the Earth. The Earth may have been completely covered in water. That's a new result. I just wrote about that a couple of weeks ago. So it's possible that Mars was habitable billions of years ago. It wound up losing its water, losing its atmosphere through various processes. So now it's dead. But the point is, just because we see a planet that's dead now doesn't mean it always was. Looking for evidence of life, finding a fossil on Mars may not be as exciting as finding an alien that's alive, but it shows us that life can exist elsewhere, which is something we don't know yet. So that also would be a huge breakthrough. So let's put all this in context. Is the Earth special? In our solar system, yes. Among other stars, maybe not. We're finding planets a lot like it. We don't know if they're Earth-like, but they're similar to Earth. There are other worlds in our solar system that could bear life. They have liquid water and could be warm enough in there for life to evolve. So in that sense, is Earth special? No. What if you have a gas giant orbiting a star in the habitable zone with a moon that is big and that has water on it? So when I said earlier that, if you find a gas giant in the habitable zone of a star, big deal. Well, it might have a moon, and that moon might be habitable. It could be Endor, the forest moon of the Ewoks from Star Wars. We don't know. So there's tons and tons of not just planets that look like Earth, but planets that look maybe nothing like Earth, but are still Earth-like in many, many ways. So in that sense, maybe Earth's not special. There are billions of planets the same size as Earth out there. There could be tens or hundreds of billions, maybe trillions of habitable worlds, habitable, who'd want to live in Enceladus where you can never see sunlight, but still potentially habitable. And that makes the Earth seem not so special. And then I look at a picture like this. This is Apollo 8, 1968, orbiting the moon and taking this picture of the Earth as their orbit brought them around the moon. They saw the Earth rising over the limb of the moon. This is the actual image. And look at that planet. That is some kind of gorgeous, isn't it? Look at the blues and the white. Is that Australia? I think so. You can see there. When I look at that and I ask myself, is Earth special? I know what the answer is. And let me show you my very favorite picture of Earth. We don't think of Earth this way, right? If you've looked at Venus or Mercury through a telescope or the moon, right? You see crescent, you see it go through phases. We don't think of the Earth that way. But of course, depending on where you're looking at the Earth, it has a phase. And this was taken by the Rosetta spacecraft on its way to rendezvous with a comet, and as another European mission. And as it passed the Earth, it took this image. And I love this because seeing the Earth in the previous picture, you're seeing the Earth in space, and it looks very much alone, and it looks gorgeous. Gibbous there. I still don't think of it as a planet when I see it like that. I don't think of it as like I think of Jupiter or Venus. I think of it as still as the Earth. You see it like this, it doesn't look much like Earth. It's blue and white, but it's that thin crescent. And that, to me, that's what says the Earth is a planet like other planets, like Venus, like Jupiter, like these exoplanets we're finding. However, it is the only one we know that has water on its surface, an atmosphere we can use. We've evolved, of course, to adapt to the conditions on Earth. But still, I live in Boulder. I'm about a mile above sea level, about 1.6 kilometers above sea level. I see mountains out my window that I went up to the top of them, I'd hardly be able to breathe. And I've been even higher in Hawaii, where it's, you're gasping for breath. So you don't have to get up too high before conditions are uninhabitable. We can't live underwater, not without help. We certainly can't go down into the earth more than a couple of kilometers, 5, 6, before it gets too hot. So, we live in this little thin shell that we've adapted to. And yet still the earth is this place that we have adapted to that so well that it is special. You change the carbon in the atmosphere a little bit. This is an experiment we're running right now that I wish we weren't. Changes the planet. If the earth gets too hot, we can't live on it. If it gets too cold, we can't live on it. The conditions we have now, by definition, are special. So if you ask me the question, is there special compared to these other planets? Maybe not. But is it special to us? The answer is absolutely. Thank you very much. Thus endeth our tale.
Well, thank you for that.
Hi, Gordon. You back on?
I am back. I
need to stop sharing. There we go.
Let's fix my camera.
How are we doing? Did I run way over?
No,
I did not.
Yes. So I guess
amazing.
Now, see if anyone has some questions.
Yeah, let's take some questions from folks. Can you monitor that?
I can monitor that. Yeah, so people can ask questions. You can either ask them through the chat, or you can unmute yourself and ask a question.
Oh, that'll be chaos.
We also have a couple of people monitoring the YouTube stream for comments there as well.
Yeah. There we go. Okay, so do we have anybody? Let's see in the question. I can look in the chat room too. Somebody's asking, have we detected water on exoplanets? And how have we detected it? Yes, boy, I really, really, really want to say yes. There's a lot about exoplanets. You know what, let's see. There's a lot about exoplanets that I didn't talk about, of course. One of them is that when it transits the star, if it has an atmosphere, some of that light from the star is going to pass through that atmosphere. Different atoms and molecules absorb different colors of light preferentially, and that acts like a fingerprint. Methane, for example, absorbs some colors, some wavelengths, technical term, in infrared really well. So does hydrogen. Helium's a little bit more difficult. I think that's in the ultraviolet. Water absorbs in the infrared and in the kind of light that we see. So if you can very carefully measure the wavelengths of light that are coming through the atmosphere of that planet, you can see what's in it. And that's been done for a lot of planets. And we've seen hydrogen and methane. And there was one I was just writing about, and I want to say that there was water in it, but I can't be sure. So I can't answer your question specifically. If somebody knows, please jump in. But if we detected it, it would be water vapor, probably not liquid water. However, we have physical models. And what I mean by that is we understand the physics kind of how a planet behaves. So if it's mostly metal and it has strong gravity, what does that mean for its atmosphere? And it's really close to its star, so it's hot. You can input all of these things and try to figure out what its atmosphere is made of. And a lot of these models can predict what we should be seeing. We are seeing planets, for example, where we should be seeing things and we're not. And they think that that's because these planets have a haze layer, kind of like Titan. Titan has a haze layer as well. Just little tiny particles that are blocking us from seeing what's going on farther down. Or they may be cloudy. They may have big puffy clouds. They may not necessarily be water clouds. They could be ammonia or something else, depending on the planet. But we can actually see a lot of these kind of effects in our data. Astronomers are fairly clever looking at this stuff, and they can actually know quite a bit about these planets' atmospheres. We're getting better at this. James Webb, the telescope that's supposed to launch in October, should do very well with this, although it's a busy telescope. They're not going to want to look at too many exoplanets, but we're building better telescopes all the time. So this is going to become a big deal. I mean, 30 years ago, we were finding these things and just discovering them. Now we're starting to dissect their atmospheres. I think that's phenomenal.
Has there ever been any oxygen detected?
I'm sorry?
Any oxygen, has it ever been detected?
We've seen oxygen on other worlds in our solar system, like Jupiter and Saturn. I don't know about exoplanets. Oxygen's a tough one to find. So I don't know. I don't think so. At least not as O2, not like oxygen on our atmosphere. Shoot, somebody just asked a question that was similar. Oh, well, somebody's asking, how do we know that liquid in Titan is methane? In one way, it stands to reason. Methane is a very simple molecule that exists everywhere. Where when it's cold and you have carbon and hydrogen, you're going to get methane. There may be some ethane as well, which is a different molecule, very similar to ethane. I'm trying to think if they detected methane in the atmosphere of Titan, and I want to think they did. It shouldn't be that hard to detect that with Cassini, but again, don't know off the top of my head. This is all kind of stuff, you know what, Google will help you there. Sometimes there's specific stuff I can't answer. But it's one of those things where it's the obvious thing. You know, it's not going to be xenon or something weird like that. It's going to be something common, and methane's all over the place in the outer solar system.
All right, William Wall has a hand up.
Yeah, I wanted to. Well, first of all, it's a great talk. I love the way you did that.
Oh, thank you.
Some planets have been detected by gravitational microlensing, and I think some have been detected like many kiloparsecs away. So, I mean, do you happen to know what the maximum distance an exoplanet has been found using that method?
So what he's asking is that, or what he's saying is that planets have gravity, and you know, stars and galaxies have gravity, and there's this thing called gravitational lensing, where if you're looking at some really distant object like another galaxy, if there's something in between us and that galaxy, like another galaxy or a star or something, its gravity will bend the light from that more distant object a little bit, and that acts like a lens, and it does all kinds of things. It distorts the image. You can get multiple images. Sometimes stars and planets will pass between us and something else, and that's called a micro-lensing event because it's a smaller object. And what happens is, because that star is moving, you actually get a gravitational lens that depends on time. You don't see it, you do see it, and then you don't see it again, because you don't see it when they're here, you do see it when they're lined up, and then it disappears again. The way the light changes depends on the mass of the object, and it turns out, yeah, there are planets just out there in space, sometimes floating on their own, sometimes orbiting a star, and we've seen them pass directly between us and a more distant star, and we get one of these gravitational lensings. Quite a few planets have been discovered that way. I don't know the number, but it's a significant number. Most of them, what you want to do is you want to look at as many stars as possible. So they tend to look at the center of the Milky Way, where there's billions of stars, and the Large Magellanic Cloud, which is a galaxy that orbits our galaxy. And you just sit there and stare at the stars for a long time until their light one of the stars' light changes in a characteristic way. And there have been planets found that way. So these are planets that are light years away. It turns out a couple of years ago, a planet was found in another galaxy. And it was actually orbiting a star, and I can't remember the circumstances of it off the top of my head because it was a long time ago, and you caught me here without, it's not in front of me, but I wrote about it, and it's a candidate. We don't know if it's a planet, but the way the gravitational lens worked out, yeah, it makes sense that it was a planet doing this. So in fact, we have discovered a planet in another galaxy. Wow, that's so cool.
Yeah, I seem to recall something like that. Yeah.
Yeah, that's pretty amazing. There was a star discovered like 9 billion light years away because of a gravitational lensing effect that amplified the light from a galaxy that far away. And an individual star, a very luminous star, was seen in that galaxy. We had no prayer of detecting it without the lens. So that's a pretty convenient thing that nature has set up for us, that we can do that. Ken Jackson has raised his hand.
These are questions from YouTube. So Peter was asking if you've used different methods for detecting the exoplanets, do they agree on the orbital periods?
Well, I haven't heard of any that haven't, and that would be really interesting, wouldn't it? You see a transit that's happening every 5 days or something, so this planet's orbiting its star really closely, but then the reflex velocity method gives you a period of 6 days. Well, that would be really weird. I haven't heard of anything like that, so I don't think so. They may not agree exactly, because there's always a little bit of slop in the observations. It's really hard to like just nail exactly the period of a planet. Sometimes we can. If it's really short, you can observe it over and over and over and over again so many times that when you average all the observations out, the noise goes away really well, and you can really determine the period of that planet. But I've never heard of anything like that happening. That would be pretty cool. If it did, that would tell you something interesting. I don't know what that thing would be. There are stars that have multiple planets, and sometimes that's hard to disentangle. You see lots of transits, but then you realize, oh, this is a big transit, and then there's a little transit, like a big dip and a little dip, and they're happening with different times. So they must be two different planets. Sometimes these planets are so close together, they interact with each other gravitationally. They tug on each other, and that changes the periods of the planets. The time it takes them to go around the star changes a little bit. It turns out if you only see one planet orbiting a star, but its period is shifting, it orbits 5 days, then 5.01 days, then 5.02 days. You're like, what's going on? Probably there's another planet orbiting that star that you're not seeing that's tugging on it. And that's called the transit timing variation method, the TTV method. That lets you discover that second planet without ever having to see it. You're seeing its effect on the planet you do see. Like I said, lots of subtle, weird ways of finding these things. Somebody asked a question, what's the nearest exoplanet? The nearest one we found is orbiting Proxima Centauri. That is the closest star to the sun. It's 4.2 light years away. It's part of a triple system, the Alpha Centauri triple system, a star like the sun with a slightly smaller orange dwarf orbiting it, and then Proxima, which is a red dwarf, orbiting the two of them. And there's we detected planet B by the reflex velocity method, which is super hard because Proxima Centauri is very dim and it's hard to measure it accurately. And it also is constantly changing in brightness. These red dwarfs do that. So that made it very tough. And there was another planet predicted. And the last I heard, it's looking really good that planet C is a real planet that exists. There's very, very tentative data, as I recall, for a third planet, D, but nobody really knows. So yeah, I mean, the closest star to the sun has planets. This is a big hint that stars have planets, that lots of stars have planets. If the closest one out of a galaxy 100,000 light years across, 120,000 light years across, and the star only 4 light years away has a planet, that's telling you there are planets everywhere.
Let's see, I have Christoph asking, what do you make of Oumuamua, or Oumuamua?
First, the pronunciation is difficult. It has that tick mark in the beginning, which is a glottal stop. So it's actually Oumuamua. And I can't do that. That's Hawaiian. It literally means first scout, like the first interstellar object we've ever seen passing through the solar system. This is a small chunk of something, we're not exactly sure what, that was discovered a few years ago, moving so rapidly that it was clearly coming from interstellar space. It came in a hyperbolic orbit, which means it came in really fast and left. It's gone. It's moving out of the solar system at high velocity. It was weird. I mean, it was, the funny thing about it is kind of like what I was just saying with Proxima Centauri. If the first thing you find like that is really bizarre, what is that telling you about the general population of these things? If this thing is 1 in a million, it seems really weird that it would be the first one we found. So it seems like it's implying that there's a lot of things like it. The problem with it is that we think that the easiest kind of objects to eject from a solar system, small objects, are these icy objects that are out there past Neptune. They're small, they're really far away from the sun. A passing star might be able to yank these things away from the solar system and send them skittering out into the galaxy. And so you kind of think that it's going to be mostly ice. If something that's icy gets near the sun, that ice turns into a gas and you get a comet. And Oumuamua didn't behave like a comet. We didn't see any of this gas. On the other hand, as it was leaving the solar system, it wasn't slowing down as quickly as it should. As it's leaving the sun's gravity is pulling on it. It's slowing down as it's getting farther away, but it was slowing down not fast enough. And it seems like that maybe it does have ice, and that ice is blowing off the comet and is actually acting a little bit like a rocket, changing its velocity. But if it were made of carbon monoxide, carbon dioxide, water ice, like comets in our solar system are, we'd have seen this gas. So why didn't we? There is this idea that it's a spaceship or a spaceship part. I feel that is not a good extrapolation of the data. I wouldn't make that leap because we haven't eliminated all possibilities yet. And in fact, the professor making these claims, when he publishes these papers and everything, he doesn't seem to be citing references about comets. There's a paper that came out that showed that Oumuamua may just be a chunk of nitrogen ice. And in fact, these could be common. Pluto has got that big nitrogen surface on it that I mentioned, Sputnik Planitia. Something smacks into Pluto, it's going to blast that stuff into space, and that can leave the sun and travel the galaxy. So there's a potential source for that. If it's frozen nitrogen, it explains a lot of the behavior of it. Maybe not everything, but it's a really, really good explanation. And it doesn't make the gigantic leap of it being a spaceship. So, for now, I'm going to go with nitrogen ice until somebody comes up with something better.
Let's see. What is your opinion of SpaceX's Starlink and other private enterprise low Earth orbit projects?
Oh my God. I should share the screen of the notes I have. I have not written about this because every time I tried to sit down and write about it, something would happen and it would change everything. Not a fan. In very, very broad sense, I'm not a fan. Elon Musk and SpaceX are launching these constellations of satellites, dozens of satellites at a time. He wants to put up thousands of these low Earth orbit satellites to provide broadband to everybody in the world. It's a noble idea in general. I like the idea of being able to get everybody online so that more people can yell at people about the way they dress or their politics or whatever. Why should we be the only ones that have that luxury? But honestly, it would be nice to get everybody with internet. I'm not going to go into the details of the problems with this, the technical problems of getting terminals to everybody and all of that. The implication here is the impact on astronomy, and it's devastating. These satellites are bright. There are a lot of them. They experimented with making them darker, and they can, but they're not dark enough. And studies have shown that big survey telescopes, which we're spending, tens and hundreds of millions of dollars on to build these things, they're barely going to be able to take any images that don't have a satellite going through them, and that's really harmful. A lot of fans of SpaceX say, "Well, we'll just get Elon to launch space telescopes," and it's like, it's not that easy. These are expensive things to build, and we would need hundreds of them, and you can't make them as big as we need them. So there's a lot of back and forth on this. And there are other companies, OneWeb, and I can't remember the name. There's another one that just threw its hat in the ring. They want to launch hundreds of these things. As much as I dislike this idea, because it's screwing up astronomy big time, it's inevitable. It's going to happen. We're always launching more satellites. It may have taken 100 years otherwise to get as bad as it's going to be in 10 years now with these constellations. Maybe this will spur us to come up with solutions. I don't know. I don't know if there is a solution. I don't like it, but it's inevitable. There are a lot of things I don't like that are inevitable. So, at this point, we just have to kind of face the fact that this is what's going to happen. What are we going to do? And I don't have the answer to that.
Well, there's also going to be a lot of space garbage, and I'm wondering how it's going to affect launches.
Yeah, I'm concerned about that too. We're talking about launching rockets every day, and we're still not really regulating what to do with them. There are rules about having to deorbit satellites now, and there are companies. The European Space Agency is doing great work on trying to figure out ways of deorbiting space junk. they've got a lot of interesting things that they're trying. But yeah, that's going to be a huge problem. Every time you launch something, there's just debris. You can't help it.
Well, even those satellites themselves, those microsatellites. That
Yeah, I mean, the
must-
cubes. Now the CubeSats are probably not that big of a deal because they tend to be in low Earth orbit, and after a few years, they just burn up. But you put them in a high Earth orbit, and these are small satellites. They're literally, shoebox sized. I'm still, I'm concerned about lost tools, flecks of paint, nuts and screws, and things like that. There's tons of this stuff up there, and they're too small to really see very well. And the more we launch, the more dangerous this is going to be. The movie Gravity is science fiction. A lot of that movie was silly, but and it exaggerated for drama. But honestly, I mean, what they were showing is the kind of thing that can happen. It's a real thing called the Kessler syndrome, where two satellites collide, they create debris which expands and hits more satellites, and you get this exponential growth. That's not nonsense. Something like that could happen. It may not happen that quickly, over the course of one orbit or two orbits. But yeah, that's a real concern. And I think we need much stricter regulation on this sort of thing, because a company may have its heart in the right place trying to do good stuff, but if they don't do it right, they could do a heck of a lot more damage than the good they're doing. We'll see.
Yeah, Phil, isn't there a private company right now launching CubeSats that are specifically designed to attach themselves to space junk and slow it down enough to drop it into the atmosphere to do a burnup?
I don't know if you could do that with a CubeSat. They're small and can't have a lot of fuel. There is an idea of using solar sails, and I'm not sure if there's a company looking into that. There may very well be. Like I said, the European Space Agency is looking into this a lot. They've been testing different ways of either attaching to satellites or almost lassoing them with a tether. There's this idea of zapping them with lasers from the ground. You hit them with a powerful laser. It heats one side of the satellite and will either vaporize material, which acts like a rocket, or uses other methods that will change the orbit of this thing so that it can safely deorbit. There are a lot of different interesting ways of doing this. I think the future there is bright. The question is it going to be able to keep up with all the junk that we're launching? That I do not know. Ask me again in 30 years. And I'll say, because I'll be too old.
Yeah, well, if I'm around in 30 years, I'll ask you.
Yeah, great.
No, but it was just something, there was a couple of different ones, and one was that would use water in the CubeSat, and it would be strictly a matter of it would latch on, and then it would slowly let this water leak out, and that would just create enough propulsion over a period of time to slow the object up that it would start to into a lower orbit.
Yeah, I heard something about that. Yeah, I'm sorry. I was thinking of ones that will stay in orbit. They'll sort of change the orbit of one satellite, detach,
No, this
and then go off
is
to another one. This would be a single-use thing.
yeah, this would be where, but because they're little CubeSats, you could throw several hundred up at once with different targets to reach, and then they would
They're not
all
cheap. CubeSats like that are still in the tens to hundreds of thousands of dollars. So I don't know how cost effective that is versus spending a couple of million or whatever to build a bigger one that can go from thing to thing. But the capitalists will figure this out. Pretty
Yeah,
good.
another one. Yeah, another one was that all future satellites would have to have a tail attached. It would unwind,
Right.
and that in itself would slow it down. By adding drag.
Yeah, there are a lot of
cause
different things like that. They have to have a deorbiting engine or something like that.
Yeah,
I think that's fine. I think, yes, if you want to put something into space, you have to be responsible for it.
yeah, because somewhere just yesterday or the day before it was mentioned that already the light, the brightness of the night sky has gone up 10%.
Yeah, I haven't read that article yet, but I saw the news about it. I need to read that. I've got a note for it someplace. Oh, I see another hand up.
Oh, yes, there is another hand up. So, Ruse.
Yeah,
Oh, there we are. Okay.
you have my audio. Yeah. So I do some planetary imaging myself, and as an amateur, we don't have the luxury of the big telescopes. But what really helps is the lucky imaging technique, where we take thousands or tens of thousands of images. Is that something that the big telescopes and the professionals do as well?
They could.
For Earth-based, ground-based?
Yeah. The idea is that the Earth's atmosphere is constantly in motion, and that's what makes stars twinkle.
Yeah.
So what you do is you take thousands of very, very, very short exposures, and what you get lucky. In one exposure, the atmosphere was steady, or you freeze out that motion, and you can see more detail. This was done in the 70s, called speckle interferometry. It's a little bit different than that. It's a similar technique. It's very sophisticated. And to image some of the bigger stars like Arcturus and Aldebaran, maybe Betelgeuse, some stars that are so physically big in space that they appear as a disk in the sky, and you can actually image the disk that way. It's really tough to do. Yeah, I mean, you could do that with nearby stars and look for planets that way. That would be super tough.
Because the adaptive optics, I'm guessing, don't work for planets?
It does. On the Very Large Telescope in Chile, which is an 8-meter gigantic telescope, there's a camera called Sphere, and it uses adaptive optics, and it's in very, very advanced techniques. When I first saw the images from it, I thought, well, these are fake. I mean, somebody made this image on their computer to represent what Sphere is seeing. It's like, no, that's an actual image. It actually it's imaged asteroids. You can see them as, shapes, and phenomenal images of stars in the sky and things like that. So, our technology is getting better at this sort of thing. So I hate to say it this way, but, the sky's the limit. Who knows what people are going to figure out to be able to image planets that way. And I think, lucky imaging. The problem with writing a blog post every day is that I read papers constantly, press releases and papers, and they blur together after a while. And I was it couldn't have been more than 2 months ago reading about the lucky imaging technique that was done for something. And I don't remember what it was. It wasn't looking for planets, but it was doing something with stars. Dang it, I don't remember. But it's a great technique. It works, so why not? You're taking video instead of an image, and then you collect the pieces and put them together. Works.
Yeah, I find for myself, it really gets a lot of resolution for a very small telescope.
Yeah,
relatively. Yeah,
and video cameras aren't that expensive.
Yeah.
I used to hook up my Konica TC. If anybody's really old, they'll remember Konica cameras. Up to my Cave 10-inch Newtonian. I had a Cave Newtonian back in the day when I was a kid, and take pictures and develop them myself and everything. I was in grad school when digital detectors came along, and then I started working on Hubble, writing my own software. And it's funny to see that we kind of hand wrote our own software to do stuff that you can buy in these packages now. And sometimes I'll see the package and it's like, oh, we're doing this technique that does this and this. And I'll think, oh yeah, how would I code that? Oh yeah, I did something like that 20 years ago. Not this efficient, or, not this great. It doesn't work that well, but it's kind of amazing to me. And so that's the reason I actually stay away from digital astrophotography now, because it's all I will ever do. It'd be like crack cocaine for me.
Yeah.
I wouldn't have a job or a family. I would be living on the street with my telescope and my computer.
Tell me about it.
Yeah, that's all I would ever do. It's addictive.
All right, thank you.
I miss it, but not that much. I'll let other people take the pretty pictures, and then I can write about them. Works out for everybody.
Thank you.
How are we doing?
A few more questions here from YouTube. Could there be water in deep caves on the moon?
There is water on the moon, quite a bit, actually. This was, I was working on Hubble was it 99? I think it was pretty late. It was right before I left and took another job, but they hadn't definitively found water on the moon yet, and they were looking for it. And the idea is that in the poles of the moon, especially the south pole of the moon, there are craters that are very deep. And because, the moon is spinning, at the South Pole, the sun never gets very high above the horizon. Just like, on Earth, you go to the South Pole in the winter, the sun never rises. The same thing's true for the moon. If you have a really deep crater, at the bottom of that crater, the sun never reaches it. It's a permanently dark area. If any water were ever on the moon, it would still be there. And there are ways of doing it. Like if a comet hits the moon, it vaporizes, the water splashes out all over the place. Any of it that lands on the south, in the South Pole in these craters would stay there. And it turns out there are other ways this can happen as well to get water there. And then when I was working on Hubble, Lunar Prospector, I think it was Lunar Prospector, was an orbiter going around the moon taking pictures. And they were going to crash it at the South Pole really hard. And hopefully if there was any ice, this would be ice here. I should say that the sun never reaches these places, so they're very, very cold. And they're so cold that any ice that's there stays there, permanently cold regions. So they smack the spacecraft into the surface of the moon. If there's ice there, it would get blasted up into space. Sunlight would hit it and break apart the molecules into oxygen and what's called a hydroxyl molecule, oxygen and hydrogen bound together. And the camera I was working on at the time, called STIS, which is a Hubble camera, can detect the hydroxyl molecule in various ways. And I volunteered to help them with that project because holy cow, if we find water on the moon through observations, I want to be the one working on it, right? And it turns out it didn't work. The observations didn't work. It's really hard to observe the moon with Hubble. You can, but it's tough. And it just didn't work. And I was really disappointed. But then a few years later, they found water on the moon. Now it's been confirmed an Indian, it was an American camera on an Indian orbiter, or an Indian camera on an American orbiter. You know what? I can't remember now. But it definitely found water on the moon. We know those craters have it. Now, we now know there's water widespread on the moon, broken up. It's trapped in minerals mostly, but it's there. It's either frozen or it's part of minerals, which makes it hard to, what do you do with, you have a rock that has water bound up in it? It's hard. You can't just crush it or squeeze it. It doesn't work that way. You have to actually extract the water out of it chemically. So that's hard. But it's there. And it wouldn't surprise me if in 25 years, that might be a little optimistic, but 20, 30 years, something like that, we're mining it. It's possible. The way NASA really wants to go to the moon, it's possible. Oh, and I should say, why do you want water? Well, you want it to drink. Carrying it from Earth is hard. You can't compress it. So it's very heavy. So taking it from Earth is hard. You find it on the moon, you can melt it and purify it and drink it. You can break it up into hydrogen, which is good fuel. You can break it up into oxygen, which is air to breathe. You can also make hydrogen peroxide, which is when it's pure. The stuff you buy at the drugstore is like 3%. It's very, very weak. Hydrogen peroxide, when it's pure, is incredibly reactive. It's actually a really good rocket fuel. So it's like the most amazing substance ever. And if you find it on the moon, it's very helpful if you want to put bases there. So I should have mentioned that.
All right. Here's another question from YouTube. How important is plate tectonics to the possibility of life?
I'm not an expert in this field, but there's this idea that plate tectonics are extremely important for a lot of reasons. One is that in the Earth's mantle, there's a lot of water. There may be up to three times as much water in Earth's mantle than there is on the surface. Again, it's locked up in these weird minerals. You can look them up. They have names like ringwoodite and I'm blanking on the other names. Doesn't matter. It may be that plate tectonics is a way of bringing that water up from the Earth and getting water on the surface down into the mantle. And that actually helps plate tectonics move. Also, so it's a good way of getting access to that water. It makes land, volcanoes and eruptions and things gives you more surface land to work with. It also brings up minerals and chemicals and things that are conducive for life. There's some arguments that plate tectonics helps life because of the way it maintains I was going to say the heat balance. I don't think that's right, but maybe the atmosphere and things like that, it keeps the Earth, all of these things in balance. And that's that. So you look at Venus with a very thick crust, doesn't have plate tectonics. There's this idea, and I think it's an old idea, and I don't know if it's obsolete or not, that every few 100 million years, the pressure builds enough that Venus cracks open, not like an egg, but it gets huge rifts in its surface. The stuff comes pouring out and resurfaces the whole planet. And you don't want that. You don't want a volcano burying your entire planet in lava a kilometer deep. And so that's what happens when you don't have plate tectonics. You want to be able to relieve that pressure a little bit. I don't know if that theory is still in vogue or not. That's about all I can say for that question. Again, this is the sort of thing where if you Google it, you'll find people who are smarter than me talking about it. Oh, somebody says lava is good fertilizer. That's true. Some of the best coffee in the world, for example, and some really good wines are grown in the acidic soil from volcanoes. It's good stuff.
All right. Another question. Is our understanding of exoplanets going to change the Drake equation?
Yeah, the Drake equation, again, like the habitable zone, the Drake equation is more of a concept than it is a hard and fast rule. It's not even really an equation; it's an inequality. But the idea is that there are a set of circumstances that you need for life to be able to exist on a planet. And so Frank Drake, who was sort of one of the founders of SETI, the Search for Extraterrestrial Intelligence, wrote these factors down. Now, for example, you need stars. And it's the fraction of total number of stars in the galaxy. If you want to find out how much life there is in the galaxy, well, first you have to know the fraction of stars that can have planets. And we're learning now that number is very close to 1. Basically, any star can have planets, and most of them may. And then the number of planets that those stars have, and that number is on average 1, roughly. Then the planets, as I was saying, the old Drake equation would say, well, how many Earth-like planets do they have? Are they old enough to support life? Do they have the right kind of atmosphere? Did life evolve on them? Did the life become intelligent? Did that life become technological, I mean? And these are all represented as a series of fractions. Out of how many planets does this planet are suitable for life? And you wind up in the end with a number, and you multiply that times the number of stars in the galaxy, which is a big number, 200 billion or something like that. And that tells you how much life, how many civilizations there are out there that we might be able to communicate with. We don't know a lot of these factors. We don't know how many planets there are. We don't know how many have life. We don't know if you have life, how many of these planets with life on them are going to evolve to the point where they become technological or intelligent, whatever you want to call intelligence. And we have no idea what those fractions are. They could be very close to 0. We may be the only intelligent technological civilization in the galaxy, or there may be thousands, or they may be so advanced. It's like, why don't we see them? And it's like, well, it's because they're all communicating with subspace hyperdrive. They're not talking using radio, and they ignore us because they don't care about us. So who knows? But discovering these exoplanets absolutely took a couple of those terms and said, yeah, we're getting a much better handle. We didn't know what they were at all before. They could be anywhere between 0 and 1. And now we have a much better handle on what they are. Now we just have the other, 10 factors we got to figure out. That'll be tougher.
Okay, let's we got one last question. Unless it comes up
Very good
during this one. Do you think life always evolves where the conditions are right, or is it accidental?
This is a tough one to answer. It's a good question. If you had asked me this a year ago, I would have said yes. And the reasoning is that we have evidence of life on Earth going back at least 3 billion years. And there's some evidence it goes back 4, maybe. Even being conservative, that means that after about 1.5 billion years, the Earth got life on it. And in the more optimistic sense, Earth got life on it. And I should say, be careful here, because what evidence are we talking about? You have to, cells they don't leave fossils behind. You find bacterial colonies, bacterial mats, stromatolites, which are bacterial colonies that have fossilized. And these can be very, very old. So if life evolved 4 point, whatever billion years ago, we may not have any evidence of it. But if you think that, life formed on Earth not too long after it cooled and had liquid water on the surface, then if it formed rapidly, then it seems to imply, right, that it's easy for life to evolve out of prebiotic materials, amino acids and stuff like that. And we know that those are common; those are everywhere. It seems like that. Yeah, my answer would be yes. It just seems like the Earth is the example. It formed right away, so it must be easy. And it turns out it's not that simple. David Kipping is an astronomer, a very clever astronomer. I learned about him because he's looking for exomoons. He's looking for moons around other planets, orbiting other stars. But he's also, he looked at this statistically using Bayesian statistics, which I have a very, very fuzzy grasp on. The math is very complicated. But he showed that life may not be as common. We can't use Earth as the example because it's the only example we have. And this is something I do understand. Just because we're here doesn't mean life is easy. Just because it evolved rapidly doesn't necessarily means life is easy. It just means it evolved rapidly here. What are the actual statistics? And what he came up with are very subtle arguments. And I'd have to read it again, even though I just wrote about it a few months ago. The arguments were subtle enough that I'd have to think about it again. But basically, he said that if you want to get to intelligent life, you probably do have to, because stars change over time. The sun is getting hotter, and in 100 million years, we'll have runaway greenhouse effect, and all the oceans will boil. So we have to figure out what to do between now and then if we want to survive. So there's this finite period where life has a chance to evolve. If you evolve early, you have more time before things get bad. If you evolve late, yeah, that window may close on you before you get a chance to do anything more complicated than banging rocks together. So I want to think that life is common. I still feel that may be the case. I have to be careful of my own biases, but all I can say is we don't know. We do not know. We're very close to being able to find out. It would surprise me if in 50 years, maybe, if we really wanted to, we could build telescopes big enough to look at Earth-like planets orbiting other stars and detect oxygen in their atmosphere or direct signs of life. That may very well happen in just a few decades. So for now, I'm just going to say it's a possibility. I want to think so, and hopefully soon enough we'll know for sure. It's a hopeful way to end, I think.
Yeah, I'm going to go one more, and then I think.
Okay.
Have magnetic fields been detected on exoplanets?
How do I answer this? Kinda. How do you detect a magnetic field? It's not that easy. It's not visible necessarily. You have to look for its effects on the planet. One thing a magnetic field does is if you have a star that's blowing a wind of subatomic particles, the solar wind, for example, the magnetic field acts like a net. It catches them and then funnels them down through the planetary atmosphere. These particles are then moving very rapidly. They hit the nitrogen and oxygen and other stuff in our air, or in the air of a planet, and it glows. And you get an aurora, the aurora borealis, which you guys probably can see better than I can. You're farther north. Although it's Vancouver, you need clear nights for that. So sorry, you're out of luck. I know what the weather's like there. So an aurora, we've seen, you can see the aurora on Earth. We've seen it on Jupiter and Saturn, for example. But aurora is not just visible light. It actually emits radio waves, another form of light, much longer wavelength. But you can detect radio waves coming from an aurora. The magnetic field can generate radio waves in other ways. Jupiter is the brightest source of light in the sky at 10-meter radio wavelengths. I believe that's true. I may be wrong. If it's not the brightest, it's one of the brightest. And that's because of its magnetic field. We have seen these effects on brown dwarfs. And brown dwarfs are objects that are in between planets and stars. It's like a supermassive planet or a very, or a very, very low mass star. It's not really a star. It's not really a planet. It's its own thing, but they have a mass sort of in between, the biggest planets and the smallest stars. And auroral emission. Wow, is that hard to say? The radio emission from an aurora has been detected from brown dwarfs in a couple. I don't know how many. It's a handful. It's a few. And so we've detected the magnetic fields of these objects. So in the paper I read just a few weeks ago about this, they said it's not impossible. I love that sort of phrasing. I believe that's called a litoses. It might be a zeugma. I can't remember the term. I love these. I love words that describe these things. Where it's damning with faint praise. It's negating a negative. So it's not impossible that we could detect a planet's auroral emission orbiting another star. It's really hard, but we may not be that far away from doing it. And if we do, then that means we've detected a magnetic field around another planet. But it's probably going to be from a gas giant and not a planet like the Earth, because gas giants can have much more powerful magnetic fields than the Earth does. Jupiter's is way more powerful than ours.
All right. Well, I'd like, on behalf of Vancouver Center, I'd like to thank Phil very much for the talk tonight. It was very entertaining.
No, thank you. I really appreciate this. I'm honored that you asked me.
Yeah, I only wish we could have had you here, at which point we would have asked you to draw and get a prize, but
ask me again in a few months. I'm getting my second shot in 2 weeks, so we'll see.
Yeah, we're still waiting for most of ours around here.
Oh yeah, I know. The rollout's different. It's craziness here too. Some states better than others. So yeah.
I got my first shot on Monday. So
nice.
Number one.
Well, in a year, spread me a little thinner. I'll come back up. Just give me some Timbits. Boy, those chocolate Timbits, man, are those good.
Sounds like he's going to be a cheap buy in the future, guys.
Yeah.
Oh, I don't want just Timbits, but that's a good start.
By the way, Ian, I see is still here. Ian, I'm looking forward to driving on your roadway in Edmonton one of these days. Congratulations.
Thank you very much. Appreciate it. And thank you, Phil. That was a great talk.
Thank you. Yeah, I was at Jasper a couple of years ago at their annual festival, and that was stunningly gorgeous up there. So yeah, I love Canada. I'm always happy to go back.
All right.
Thanks very much.
Thank you very much. Thanks, everyone. So we'll be doing this again next month. Should have written down what the name of our speaker was. But yes, we will have another speaker. And yeah, invite everyone to join us and check it out. And with that, we'll call it for tonight. And again, thank you very much, Phil, for the presentation. And yeah, see you all in May.
Good night, everybody. Thanks again.